In this video, we present a tool for interactively exploring the configuration space of a planar robot that navigates static planar obstacles. Configuration spaces can be difficult to grasp initially, and the purpose of our software is to illustrate the relationship between a two-dimensional physical space and three-dimensional configuration space. The visualization is built from an exact parametric representation of the surface of the free space boundary. The method for constructing this representation is described in previous work that we do not discuss here. The visualization software presents interactive 2D and 3D views that allow a user to experiment with the robot's configuration. We model the robot and obstacle geometry using circular arcs. Arcs are parameterized by normal angle alpha in the standard manner, and they are useful for efficiently representing curves. It's still possible to approximate straight edges using large radii, as shown in this obstacle. In this 2D scene, you can see the robot's boundary in red and an obstacle's boundary in gray. The obstacle envelops the robot and consists of the infinite region outside the gray boundary. Using a mouse, the user can pan the view and zoom in or out to focus on different parts of the scene. The robot can be translated by dragging it with the cursor, and its rotation can be set by creating an angle between the cursor and the robot's origin. We are interested in visualizing the valid placements of the robot. For a fixed orientation, this free space is the set of translations such that the robot does not overlap the obstacle. It is bounded by arcs called subedges, also parameterized by alpha, that exist where a robot and obstacle edge make contact. The subedges are shown in green. The contributing edges from the robot and obstacle can be checked by translating the robot along the free space boundary. Notice how the robot remains inside the obstacle so long as it is not moved outside the subedges. The subedges illustrate the cross-sectional boundary of the free space for the robot's current rotation, theta. The translational free space is dynamically visualized as the robot's orientation changes. Notice how the robot always has plenty of space to translate within the two rooms of the obstacle, but there is a small bubble of free space that traverses the corridor, corresponding to the highly constrained motion required to move from one room to the other. We now move on to the three-dimensional visualization to see the entire free space at once. The green surface illustrates the free space boundary of the previous scene for all orientations of the robot. The horizontal XY plane contains the same 2D cross-sectional views we saw earlier, and the vertical axis is used to indicate the robot's rotation. For reference, the 3D arrows colored in red, green, and blue indicate the X, Y, and Z axes respectively. The user can fly the camera throughout this space to explore this surface from both outside and inside the free space. The Z dimension, corresponding to the robot's rotation, extends indefinitely in our 3D view. However, the geometry is periodic and wraps around every 2 pi. The surface exists roughly between negative pi and positive pi. If we draw planes at negative pi and positive pi, you can see the surface is not exactly clipped at these values. This is a consequence of how we construct the surface. To emphasize that the surface is periodic, we will temporarily render copies of the surface shifted by multiples of 2 pi. This view renders the 2D scene and 3D scene side by side. You can see the 2D cross-sections highlighted in 3D while the rest of the surface is translucent. Alternatively, the 3D surface can be clipped above the robot's angle, theta, such that the 2D cross-section appears at the top of the 3D surface. The robot, which is a shape in 2D, becomes a point configuration in 3D. This configuration is its x, y, theta coordinates. The robot configuration is visualized by the intersection of the 3 red lines. Notice how the 2D robot is just touching the obstacle surface as this point makes contact with the green surface in 3D. As long as the robot is on or inside the 3D surface, the 2D robot is not colliding with the obstacle. While we have an exact trigonometric representation of the surfaces you see in 3D, some processing is required to actually render it on screen. For interactive graphics, the standard approach is to rasterize polygonal meshes, so we approximate the surface using triangles. The normal vectors for the vertices of each triangle are calculated from the exact representation, not the triangulated one, so the smoothness is preserved even with a coarser triangulation. Here you can see several triangulations of the same surface with varying granularity. Notice how the shading and overall structure remain similar, even with many fewer triangles. Recall from the 2D visualization that subedges exist at the boundary of the free space and are parameterized by alpha. Subedges arising from different orientations of the robot are identified if they correspond to the same robot and obstacle edge contact, and if their two neighbors are related in the same fashion. We call a collection of identified subedges a sub, which is parameterized by both alpha and theta. Here you can see each sub viewed as a randomly colored curved trapezoid in 3D. The subs are triangulated as follows. First, samples are calculated along the sides of the subs. These are the ends of the arcs in 2D. Next, samples are calculated at the bottom and top, or start and end events respectively. Finally, samples are regularly placed between the sides of the sub. Care is taken to ensure samples are unique and shared with neighboring subs to prevent gaps in the mesh. We then perform a triangulation of these samples in alpha-theta parameter space, where the sub is a standard trapezoid. We can generate paths for the robot using both the exact geometry and the triangulated approximation. Here you can see the 2D robot transition from one side of the obstacle to the other. With a combination of translation and rotation, the robot successfully passes through the narrow tunnel. This particular path, shown in white, was created by moving along the edges of subs in 3D. With a triangulated mesh, custom paths can be calculated by performing a breadth-first traversal of the triangles. The user can select a starting and ending configuration for the robot. The green robot indicates the start, and the red indicates the goal. We'll show a few more scenes that demonstrate the variety of visualizations that can be produced. Here is a scene that is very similar to the prior one, but several edges are near linear to demonstrate how large radius circular arcs can be used for straight-edged shapes. In this example, the robot consists of 3 disconnected parts that can rotate within a very limited space. The resulting configuration space surface is far smaller. The clearance here is about 1 part in a million. Some similar scenes follow with equally restrictive free spaces. The final scene has the robot on the outside of the obstacles. The robot is free to move around almost anywhere, but the shorter path through this forest of obstacles requires some tight bottlenecks. It is much easier to view these bottlenecks when the camera is positioned outside the free space.